But there are definitely trends among families, and we got with the van der Waals equation that every substance should have the same Z critical, but that's not true. But we can create, this is a corresponding state chart, PR, DR versus Z. Yeah, that's a corresponding state chart.
That's not for the cubic function, right?
No, that actually is from experimental data. This relationship should hold experimentally, okay? We got that from the van der Waals, but this is experimentally. If you have T reduced, P reduced, you should be getting the same Z. And all the points that you see are experimental data. The solid line is the average of hydrocarbons. The solid curve based on data for hydrocarbons. But you can see some clear trends. That, for example, here, clearly you're below what you get for hydrocarbons. Okay, so you definitely see some trends. And yeah, once I turn on the projector, I put the sunglasses. So that means really that you would do much better if you included Z critical. So what people have done, they have developed Z charts for Z as a function of P reduced, T reduced, and Z critical. Z critical is not always very well known, particularly the P critical, T critical is generally known, but V critical is not always known. So the alternative is to use the eccentric factor. And the eccentric factor is obtained by matching the vapor pressure at reduced temperature 0.7. So you have an extra parameter that you use it to match vapor pressure at a specific reduced temperature 0.7. Vapor pressure at T reduced 0.7 divided by P critical. In other words, P reduced 0.7. P vapor, this is the reduced. Okay? Now, we have developed expressions for the departure enthalpies, and so on. And one expression that we got, 6422, is that the departure enthalpy at any temperature pressure is equal to integral T comma P equals 0 to T comma P of R, of V molar minus T partial V molar with respect to T at constant T dP. Substitute in it that V equals RT over P times Z of T reduced, P reduced. What are those? Oh, sorry, let me backtrack a little bit. I mentioned before that you would get better if you include Z critical, and the second plot shows you the same information, compressibility factor against P reduced at different T reduced. So these are different T reduced. But this is made specifically for Z critical equals 0.27. You can see up there Z critical equals 0.27. And what would be the critical point? The critical point is right there. Here are two phases in equilibrium, saturated gas, saturated liquid. And at the critical point, the two come together. So the critical point is here. And you notice, of course, T reduced is 1 at this point, and T reduced is 1. So the critical point is right here. 0.27 is where it would be. Okay? So we have charts of Z as a function of P reduced, T reduced, which you can translate into functions. You can differentiate numerically, right? So when you have an expression, you have this derivative here. I can calculate it numerically. The chart gives me Z of T reduced, P reduced. That's what this chart gives me. Coming okay? This chart gives me that. So I can plug it into this expression, differentiate numerically, and therefore I can get a chart of the departure enthalpy. And actually, people have done that and charted it, and it's more convenient to plot it not as H reduced, but as H reduced over T critical. So from here, you will get an expression that H minus H ideal gas at Tp over T critical is equal minus, if you manipulate this, put it in here, do the algebra, you get minus RTR squared integral PR equals 0, PR of 1 over reduced pressure partial of Z with respect to reduced temperature at reduced pressure dPr. So you can calculate that numerically. And after you do that, you can put the results to this chart. What do we have here? Departure over T critical as a function of reduced pressure at given temperatures. Here is the critical point. 1.
When you write T and P next to the difference in H's, what is that? Are you saying that?
At a given temperature and pressure. Or TRPR equivalent. Okay, you can write TRP.
At a given temperature and pressure?
Yeah, this is the expression at a given temperature and pressure.
Okay.
Which can translate a given TRP.
That's what I thought. Yeah, it looks like it's constant.
What looks like it's constant?
Like when I first saw it, I'm like, constant T and P.
We have been writing it like that, I wrote it like that for a long time, and that's how also your text writes.
Right.
So that's why I've been following pretty much your text convention. Okay? And we can do the same thing with enthalpy. By the way, okay, I can give you an equation number for this. This is, no, I can't give you. But we can do the same thing with entropy. And starting from 6,423 for entropy. And that will give us that just T reduced, P reduced equals minus R integral T reduced, P reduced equals 0 to T reduced, P reduced of Z minus 1 over P reduced plus T reduced over P reduced partial Z with respect to T reduced at constant P reduced dPr. And as you might guess, the next figure that I have here is it. Okay, here's the equation I just typed. 6611. Okay, actually I've given equation number, so 6611 for this one. And here's the result of the chart. Again, you have gas, liquid, okay? Each line is at a specific T reduced. And these are all for Z critical 0.27. both the enthalpy that I showed you and the entropy I'm showing you now are at z critical point to the sun. Yes, sir.
So basically, we're normalizing the departure with respect to the reduced variables. What exactly?
No, that means you mean this?
Yes.
Well, you can consider function of TP or TRPR. Doesn't matter. From any TRPR, given T critical and P critical, you calculate TP.
Gotcha.
So you can either see it as a function of T. The chart gives you a function of TRPR because the chart has TRPR.
Okay.
So TRPR is more correct, but once you know for TRPR what it is, you know what it is for TP. Or you can translate. You're interested in a TP. Translate your T and P into TRPR. Right? That's how it works. You have a substance, you need to find T critical, P critical. Where can you guys find T critical, P critical for a lot of substances? Very easy. Hmm? What is it? Back of the book, not that many.
User?
Unison, for example. Okay? NIST is a very good site also. All right? Clear, everyone? All right. We worked and found the relationships between, we found a specific Z critical and the relation between T reduced and P reduced from using van der Waals equation. But we must have the relationship that the partial of P with respect to V at the critical point is 0, and the second partial is 0, for any cubic equation of state value. And the algebra that I did gave me equations for A and B. Which is only if you do the same thing using SRK or Peng-Robinson, you'll also get numbers. Remember, A of T though is a function of temperature. So let me specifically talk. Okay, we're done with this part. So let's go back to so forth. Peng-Robinson, SRK, etc. must also satisfy. Right, I have another 2 minutes. Partial P with respect to V at critical conditions equals 0, and second partial of P with respect to V at critical conditions equals 0. As well as equation of state at critical conditions. If you do what we just did for Peng-Robinson, we would find Peng-Robinson. Okay, P stands for Peng-Robinson. We would find that A at T critical, remember, A is a function of T. We calculate things at T critical. So this will give me the value of A at T critical. Remember, I found an A and a B in van der Waals. The same way, I find that A at T critical is going to be 0.45724 R squared T critical squared over P critical. And B equals 0.07780 R T critical over P critical. Remember when I gave you the Peng-Robinson model? Remember I had some numbers there. Those were the numbers that you saw there. That's how they are obtained. That's what was behind those numbers that you saw for the expression for A of T. And then what you do is you express, so A is a function of T, but we know we have the restriction that at T critical it must be equal to that. So we express A of t as A at t critical times alpha of t, and then he expressed alpha as one plus the kappa which now we call reduced, of course, squared, and etc. But that's where those numbers come from. And you saw SRK, we had similar with different numbers. Solving those two equations gave us different numbers for SRK. Okay. Just one last thing, but I better stop. Those of you who came late, I distributed homework 1. Please stay to get back your homework. And also, those of you interested, I will distribute back the homework. I will do the balances with different control volume for the problem I just did. Do it both with entropy and enthalpy. So let me read the name. Daniel, I saw you come in. Where are you? Daniel, I have your homework here. Victor, I have your homework. Jamal, I have your homework. Yeah, Tao is there. Give your homework. Diana, give your homework, by the way. Sid, I saw you here. Daniel.